Welcome to this course on manufacturing for turbines. So in this lesson 11 of this course, we will see further details about manufacturing of gas turbine blades. So this lesson will cover the hot isostatic pressing which is used to consolidate the microstructure of the gas turbine blades. So in the hot isostatic pressing, we will see what is the healing mechanism, advantages, application and effects of hot isostatic pressing on such gas turbine blades. Next, we will look at the requirement of machining processes, classification of machining processes and objective of machining in gas turbine blades. So we start with the hot isostatic pressing. So hot isostatic pressing, it is one of the material processing method where we compress the components by applying high pressure and temperature from all the sides at the same time. So here basically what happens that uh, the gas turbine blade which is obtained after casting may have some defects like pores or maybe internal some defects. So it is very much required to heal up those defects or pores. So in this regard, the hot isostatic pressing becomes a very important process. So if you look at a typical diagram of a gas turbine blade, so here what we will see that as the requirement of gas turbines is increasing, size of the gas turbine is increasing. So whenever we try to cast large objects, so there is a possibility that some defects may creep into while the casting is done. So here in hot isostatic pressing, what we want to do is we want to heal up those pores or maybe some defects by applying heat and pressure. So this heat is applied of the order of several hundred degrees or maybe up to 2000 degree of temperature, and this temperature at which the hot isostatic pressing is conducted is also known as the soaking temperature. And there is also application of pressure of the order of several tens to up to 200 megapascals at the same time. So here importantly what is happening, application of heat and pressure, this is simultaneous, and this is also from all the directions. So this means that in this facility which is needed, or we can say a furnace which is needed for hot isostatic pressing, so this is not like any generic furnace, but it is a sort of a pressure vessel. So we can see the enclosure of this furnace is a cylindrical pressure vessel. So pressure vessel is basically used so that it can handle this high value of pressure and temperature. So in this pressure vessel we have a heat insulation which is indicated by this blue color. So this heat insulation, it basically ensures that there is minimal heat loss to the surroundings. Then at the bottom of the furnace we have a support on which the component which has to be subjected to hot isostatic pressing is placed, and then surrounding this component we have several heaters or heating coils which will be heating and providing the required temperature which is needed for hot isostatic pressing. And to apply this isostatic pressure, that is same pressure from all the sides, and it is remains constant during the process. So this pressure is applied using a inert gas, that is argon. So this pressure of 200 MPa, it is maintained by pressure of argon here, and this argon is introduced into the furnace using this gas inlet, and subsequently the material is subjected to hot isostatic pressing. So we understand now the need. So need, as we have now understood, understood is basically to heal up the micropores or micro defects in the cast gas turbine blades. So this is the need. This is the process where we are simultaneously applying heat and pressure from all the directions. Now here important aspect is when we are applying the heat or pressure, particularly the pressure from all the directions as indicated by these arrows here. So what happens, the near net shape of the product, it does not change. So if pressure is not applied uniformly from all the directions, so say we can say from one direction the pressure is high or from some other direction the pressure is low. So what will happen, because of this non-uniformity, some face or some side of the component may be deformed more than the other side. So in that case what happens, the near net shape of the component is disturbed. But in hot isostatic pressing, as same pressure is applied from all the sides, so the near net shape of the component is remain constant. Although it is also observed that in hot isostatic pressing, the overall dimensions they slightly reduce compared to the component which is not hot isostatically pressed. So now if we try to understand the mechanism how the hot isostatic pressing process works. So hot isostatic pressing process, it works on eliminating internal voids and microporosity by combination of three mechanisms, which is the plastic deformation, creep and diffusion bonding. So essentially it is the diffusion which is taking place because of high temperature. This diffusion is basically is enabled, and in creep, here this creep, basically in creep also we have two varieties of creep taking place. So one variety of creep is Nebaro, herring creep, and the other creep which is taking place here is the Cobble creep. So the fundamentally both of the creep mechanisms are also different. So the Nebaro herring creep is a process by which we can say the atoms and vacancies they flow through the lattice. While in the Cobble creep, what happens? It causes diffusion along the grain boundaries. So because of this, so essentially both of these things are largely dependent on diffusion, and diffusion, as we know, is a thermally activated process. And because of this, what happens as shown here in this healing mechanism of porosity in hot isostatic pressing treatment. So here we can see that the dotted line, they show the vacancy diffusion along the grain boundaries, okay, and solid line shows the diffusion, bulk diffusion of the grains into the vacancies. So we can see the interplay of Nebaro herring creep as well as the Cobble creep taking place while the hot isostatic pressing treatment is done. And this basically results in healing up of this porosity which was there in the beginning, and in the end we can see the porosity has healed up, although the grain size has slightly reduced because of the healing up of the porosity and filling up of that pore region with the surrounding material. Now, as this hot isostatic pressing process is dependent on diffusion, so all of this hot isostatic pressing is also conducted using a standard heat treatment cycle. So, for example, here for a typical nickel based superalloy denoted by K452, so here it is shown a standard heat treatment cycle for this alloy while it is subjected to hot isostatic pressing, wherein the alloy is heated up to a temperature of 1170 degrees centigrade in 4 hours, and then it is furnace cooled denoted by FC at the rate of 15 to 30 degrees per minute, after which again it is heated to 900 degrees centigrade, then air cooled, then again heated to 1050 degrees centigrade for 4 hours and air cooled to 850 degrees centigrade, and then it is kept at 850 degrees centigrade for 16 hours and subsequently again it is air cooled. So what we can understand is that every component, every product, every material will have its own optimized standard heat treatment cycle on which the hot isostatic pressing treatment will be done. Additional to this temperature requirement, there will be also requirement what will be the pressure of the argon gas, because the pressure of the gas also plays an important role, because it is ultimately the pressure of the gas which is being applied from all the sides. So after understanding this mechanism of hot isostatic pressing, we look at the role of the argon gas. So argon, as we know, this is a inert gas. So the advantage of using the inert gas is that it is unreactive to the components which are subjected to hot isostatic pressing treatment, because already in hot isostatic pressing treatment the temperatures are much higher, and the argon, it basically facilitates the application of uniform pressure from all the sides, and because of its inert behavior it does not react with the component, so no degradation of the component takes place. So what happens, the argon gas at 1000 degrees centigrade and under say intense pressure of 98 megapascals, it is likely to cause intense convection. So intense convection is much different than the convection that we know, because at higher pressures the molecules of argon will be very near to each other, and of course these molecules of argon, when they are very near to each other at elevated temperature, so they are likely to conduct or convect heat at a faster rate, thereby increasing the convective heat transfer coefficients. So heat transfer coefficients, therefore they become much higher than any ordinary electric furnace which is used for other heat treatment processes. And this we can see from these figures, where we can see the density of argon gas, it increases because this is compressible, so it increases at higher pressure of 98 megapascals, because of which the rise in temperature in this case is much faster compared to when it is at atmospheric pressure. This can be understood by looking at the slope of this curve. Secondly, we can also see the rise in temperature also as a function of with the viscosity, coefficient of viscosity of the argon, wherein we can see that at higher pressures, so there is much higher rate of increase in temperature because of the intense convection, as the nearby molecules of argon at higher temperature, higher pressure are likely to cause faster rate of heat transfer than atmospheric pressure can cause. So if we can now summarize the advantages of hot isostatic pressing treatment. So we can say that hot isostatic pressing treatment results in densified castings which show improved strength and ductility, and this improved strength and ductility is reflected in the fatigue performance because of removed porosity and refined grain structure. We can say that hot isostatic pressed parts or hipped parts generally have consistent material properties because now what has happened across the dimensions of the product, the microstructure is uniform and is refined. The hot isostatic pressing can also be sometimes used to remove in-service porosity. So what we mean by in-service porosity is sometimes that some products, they may not have reached the end of their service life, rather the service life may be remaining, and we can also utilize the advantages of hot isostatic pressing to rejuvenate the microstructure of such products and or castings, which may further extend their service life by again removing micropores and voids. So we can say that hot isostatic pressing can be an effective way to repair porous castings, or yield of casting improves because the rejections may reduce, because if we encounter small volume of pores or defects, they can be repaired using hot isostatic pressing rather than completely rejecting the casting, which will improve the yield of the casting process. Hot isostatic pressing treatment, it can be a cost saving method with negligible production of scrap, and it can be also used to reduce the quality assurance costs because it helps to rejuvenate the microstructure, repair the microstructure, refine the microstructure and improve the properties of the products. On the right hand side, we can see a typical canister or a pressure vessel which is generally used for hot isostatic pressing. And by looking at this image, we can see that the thick walls of this pressurized canister can be very well used to house the component as well as the hot gases at elevated pressure, and thereby cause the hot isostatic pressing treatment. Other than rejuvenating the casting or repairing the casting gas turbine blades, we can see other applications of hot isostatic pressing. So these applications include pressure sintering of powders, diffusion bonding of different materials, because sometimes dissimilar materials may also be joined with diffusion bonding, removal of residual pores even in sintered items, removal of inner defects in casting, rejuvenation of damaged parts, especially by fatigue or creep. Sometimes some micro cracks may also have generated under the influence of creep and fatigue, especially in rotating components. So we can rejuvenate the microstructure by subjecting them to hot isostatic pressing treatment. High pressure impregnation of carbonization method. So sometimes some carbon based materials may need to be impregnated on the surface of any other material. Again, in this case, to impregnate the carbon, the application of hot isostatic pressing can be done, but here it has to be noted that this impregnation will be only a few microns on the surface of the product, not across the bulk. So we can see that in hot isostatic pressing, as we were discussing earlier, since pressure is uniform, pressure is applied from all the sides, so the net shape of the product, it remains constant. So here we can see that there is a almost I can say 80 90 to 80% reduction in the dimension. So this part is subjected to hot isostatic pressing, and this is non hot isostatically pressed part, where we can see there is a slight reduction in the dimensions of the part, but the overall shape, it remains constant. Here we can see another evidence how hot isostatic pressing can help to minimize or close in the pores and cracks in additive manufactured parts, which can further improve the mechanical strength and here the image is captured using X-ray tomography, and which is showing a pore before hot isostatic pressing, and we can see this pore has almost healed up, and after the hot isostatic pressing the presence of pore is not there. So other than the applications we have seen, we can see some other specific applications where the hot isostatic pressing can be used, especially with powder metallurgy parts, steels, etc., with nickel-based superalloys, titanium-based alloys. It can also be used in nuclear fuel assemblies with boron fiber aluminum alloy composites, which are used in space shuttle. Then it can also be used to remove residual pores in sintered items like cemented carbides, cutting tools, etc. Removing of inner defects of casting, especially with nickel-based superalloy, jet engine turbine blades, titanium alloys. It can be used to rejuvenate parts which are damaged by creep or fatigue, especially with the superalloys as we have been discussing. And impregnation is much needed in case of say carbon composites, so there also the hot isostatic pressing treatment is helpful. So here it is tabulated the summary of the main materials which are used in hot isostatic pressing treatment, and the required temperatures and pressures are shown. So for the nickel-based superalloy, which is primarily used to make the gas turbine blades, we can see the temperature of the order of 1100 to 1280 degree centigrade, and gas pressures of 100 to 150 megapascals are used to conduct the hot isostatic pressing treatment. Next, we can see the how hot isostatic pressing treatment can improve the creep fatigue life, which can improve the creep fatigue life by 1.3 to 3.5 times, improving the elongation. And here, the different nickel-based superalloys which are used to make the gas turbine blades, like Inconel 738, Rain 77, Inconel 792, Rain 80, are used with casting, and the other state is casting plus hot isostatic pressing, and we can see there is improvement, almost 1.3 to 3.5 times improvement in the creep fracture lifetime, and of course the elongation and contraction have also improved in most of the cases. So next, we would also like to talk about the requirement of machining processes for the gas turbine. So what we have covered up to now is basically the casting. So in casting, we have seen that the mold development for the gas turbine blade is done using investment casting, and then the investment casting, these are further subjected to other specific furnaces like the Bridgman furnace. We have seen the use of liquid metal cooling process, gas cooling casting process, dipping and heaving process. The objective of utilizing all these furnaces is basically to develop a single crystal cast gas turbine blade so that no grain boundaries are present to minimize the possibility of creep failure. Then we have seen after casting the utilization of hot isostatic pressing, which is primarily used to remove micro level defects of pores or voids inside the casting to improve the microstructure and refine it. So these two processes, they come in the category of the primary manufacturing processes for the gas turbine blade. So the next process, that is the machining process for gas turbine blade, so they come in the category of secondary manufacturing process for the gas turbine blade, and we will see the requirement of machining in gas turbine blade. So in general, machining is very much essential for parts which are manufactured using casting or maybe forming, because many a times machining is needed to control the dimensional accuracy and surface finish of such parts. Machining also facilitates the interchangeability of part with proper function and reliability. And machining in generally is a subtractive process which involves removal of material from the workpiece in order to produce a specific geometry at a defined degree of accuracy and surface finish. So machining is a very wide term in manufacturing, and most of the material removal processes, they come in this category of machining. So machining is further classified based on traditional machining or non-traditional machining. In traditional machining, we know that there is a physical contact between a cutting tool and the workpiece, and because of the inherent high hardness of the tool, material removal takes place from the workpiece. So all the conventional machining processes are further classified based on cutting or mechanical abrasion. So in cutting, we can have different processes for circular shape, which include turning, boring, drilling, and for all other shapes, we can have milling, planing, shaping, broaching, sawing, filing, gear forming, gear generation. Mechanical abrasion based processes are primarily focused to improve the surface finish, which utilize either the bonded abrasives or loose abrasives, where grinding, honing are coming in the category of bonded abrasives, while loose abrasives, they involve use of polishing and buffing. In non-traditional machining, so energy in some other form, like the use of abrasives, use of temperature, use of plasma, use of laser, electron beam, etc., is utilized to again remove material. So in this case, we have various processes listed here, which include chemical machining, then we have electrochemical machining, electrochemical grinding, electric discharge machining, laser beam machining, abrasive jet machining, water jet machining, plasma beam machining, and ultrasonic machining. So we can see that there are wide variety of machining processes, but the question arises, which machining processes will be used for gas turbine blades and why? So we will see this now. So in the gas turbine blades, as we know, we are already utilizing the nickel waste superalloys because of their properties of retaining their strength and hardness at elevated temperature. So the conventional machining processes may not economically machine such materials. So these new materials, they are generally processed or machined using non-traditional machining processes, because in non-traditional machining processes, they are able to meet the stringent requirement of machining complex geometrical shapes with high precision and accuracy. So in the non-traditional machining processes, again we have different classification based on the action of the processes, which include mechanical action, thermal action, and electrochemical action. And here also, in for the gas turbine blade, the electric discharge machining and laser beam machining are primarily used to carry out the machining on such gas turbine blades. Now, question is where such machining is needed. So here we can see some images of the gas turbine blades, where we see the presence of these holes, which are known as the film cooling holes. So the need of machining process is to create this film cooling holes, and use of electric discharge machining and laser beam machining has been very popular to make these holes. And these holes basically, they increase the surface area of the gas turbine blades, thereby improving their cooling, and this also enables the gas turbine blades to operate at higher temperatures, thereby improving the overall thermal efficiency of the gas turbine. So Now we understand the objective of machining in gas turbine blade is to create these holes, and the processes which are specifically used to do that are electric discharge machining and laser beam machining. So we will see the details of this process in the next lesson. So we will now summarize what we have covered in today's lesson. So in today's lesson we have summarized the hot isostatic pressing treatment, which is used to rejuvenate and repair the microstructure of the cast gas turbine blades. Then we have understood the need of machining in gas turbine blades. We have looked which processes are there. So primarily we will be dealing with electric discharge machining and laser beam machining. And in the need we have discussed for the development of film cooling holes. Machining process is essential for the gas turbine blade. So next lecture we will cover the details about the electric discharge machining. Thank you.